Hey everyone, welcome back to the channel. Today we are diving into something super cool, modeling a 2D spring mass system using Python and GlowScript. We will go from raw experimental video to a full simulation of system in motion, comparing real-world results with physics-based predictions. Let's get started. So the purpose of this lab was to understand how a mass on a spring moves, not just by watching it, but by modeling it computationally. We filmed a real spring mass system, analyzed the footage in Tracker, and built a simulation in GlowScript to see how well our physics matched reality. At the heart of this, Newton's second law and Hooke's law. Let's set the stage. We are working with mass of 0.046 kilograms, a spring constant of 6.8751 Newton meter, and a natural spring length of 0.126975 meters. We pulled the initial position and velocity from the first frame of a tracker video to make sure the simulation starts as closely to reality as possible. Our model includes two main forces: the constant gravitational force pulling downward, and the spring force which follows Hooke's law and always pulls mass back towards the equilibrium. We calculate the net force applying Newton's second law and update position velocity with Euler's method, one frame at a time. Here's where the real physics meets code. This is the core of a simulation. Acceleration equals net force over mass. Velocity updates over time, and the position follows right after. It's a simple numerical method, but when repeated rapidly, it generates continuous, lifelike motion. Before we could compare reality with simulation, we had to process our experimental data. We took the tracker CVS file, removed unnecessary columns like time and headers, and formatted it to match the GlowScript's input needs. In the simulation, red dots show the real data points, and the blue dots show the model's prediction. Here's the payoff: side-by-side animation. You can see the blue simulated path and the red experimental path moving together. While they don't align perfectly, the general pattern is very close. That's because the simulation doesn't include factors like air resistance and human tracking error. Now let's break it down. The X position over time shows horizontal oscillation. Then why position over time reveals gravity's effect along with the vertical spring motion. The shape and timing of the curves are really similar, but small deviation tells us how real world differs from our ideal model. So what if things were different? What if the spring was softer? The mass would oscillate more slowly with larger swings. What if we had air resistance? It would dampen the motion, which our model doesn't count for. What if we misaligned the tracker's origin? The red and blue dot would be offset, something we struggled with our setup. What does it mean? If our dots don't match exactly, it means the physics is working, but our initial conditions or coordinate system needs refining. Despite the imperfections, we captured the key physics beautifully. This lab was all about bridging theory and reality. By combining video analysis, numerical modeling, and a dash of debugging, we created a working simulation grounded in Newtonian mechanics. Shout out to Georgia Tech for the lab framework, Tracker for the video tools, and GlowScript for the video and visual magic. If you liked this breakdown, drop a like, hit a subscribe, and stay tuned for more physics powered coding content. Thanks and have a good one.